Hello there, and welcome to the Sleepless Scientist, a quiet corner of the cosmos where curiosity can rest, and knowledge becomes a soft lullaby for the night. Tonight, we'll drift together into one of the most delicate ideas ever imagined: nothingness. What is nothing, really? Is it emptiness? Is it silence? Or could it be that even nothing has a story to tell? Before we begin, if you find these quiet explorations soothing, I'd love for you to like this video, maybe subscribe, or simply leave a little note in the comments. Tell me where in the world you're listening from, and what time it is for you right now. It's always comforting to imagine us scattered across the globe, each wrapped in our own small moment of night, listening under the same stars. Now, take a moment to breathe. If you can, dim the lights, maybe turn on a small lamp or the soft hum of a fan. Let your eyes grow heavy if they want to. There's no rush here. Tonight's story begins with a grain of sand and ends with the quiet rhythm of the universe itself. Imagine just for a moment that our sun is the size of a single grain of sand. Hold that image gently in your mind. A small warm speck of light sitting on your palm. Around it, in every direction, float more grains. Over 200 billion of them. Each one a star, each one with its own worlds, moons, and maybe someone else looking up at their night sky, wondering the same things we do. Together those grains form what we call the Milky Way. But even our Milky Way, this great river of light flowing through the night, is just one of 100 billion galaxies, scattered across the cosmos like dust in sunlight. The numbers are so immense that they almost lose meaning. There are quite possibly more stars in the universe than grains of sand on every beach of Earth combined. If that thought feels too big, that's perfectly fine. Let it wash over you gently, like the sound of waves at a distance. What matters is not the numbers, but the quiet realization that from this single world, this tiny patch of sand drifting around a modest star, humanity has somehow managed to glimpse the vastness of everything. It's one of our species' greatest accomplishments, though it began very simply. Not with rockets or machines, but with eyes looking upward. For thousands of years, people stood beneath the same sky you see now, sometimes warm, sometimes freezing, and asked the same soft question: what is all of this? For most of human history, the answer seems straightforward. Above the clouds stretched a grand dome glittering with fixed lights. The stars, people thought, were set upon a crystalline sphere, perfectly ordered and eternal. The heavens revolved around Earth, and everything had its place. The sun, the moon, the wandering planets, all circling within their glassy shells. It was a comforting vision. The night sky, after all, looked peaceful and unchanged. To ancient eyes, those tiny points of light were perfect symbols of permanence. They flickered, but they never fell. And so, for centuries, people lived inside a kind of cosmic snow globe, enclosed, protected, and certain. But certainty has a way of cracking. Sometimes all it takes is one new light in the sky. In the winter of 1572, people across Europe looked up and saw something impossible. A new star, brighter than Venus, had appeared among the familiar constellations. It shone even in daylight, a strange white fire against the blue. To some, it was a sign from heaven, to others, a terrifying omen. Priests wrote sermons about it. Scholars whispered that perhaps it was the same star that once guided travellers to Bethlehem. Whatever it was, it didn't fit. Among those who noticed was an Englishman named Thomas Diggers. He wasn't a famous scientist, not yet, but a curious soul with a telescope, a stack of notes, and a restless imagination. His mentor, the mathematician John Dee, suggested that maybe this new light was a star moving closer, and then fading away again. That turned out to be wrong, but the mistake planted a deeper idea in Diggers's mind. If the heavens could change, if new stars could appear where there had been none, then maybe the sky wasn't a perfect shell after all. Maybe the stars weren't fixed jewels on a ceiling, but distant suns scattered through endless space. 4 years later, Diggers published a small book, a translation of Copernicus's on the revolutions of the heavenly spheres. On one page, he drew a simple diagram, almost an afterthought, but that single drawing changed everything. In Copernicus's original model, the sun sat at the centre, with the planets circling around it and the stars forming a final outer shell, the firmament. Diggers erased the edge. He took those stars and scattered them outward into infinity. For the first time in Western history, someone dared to imagine that the universe had no wall, no ceiling, no boundary, that it stretched forever. That idea, infinity, was breathtaking and terrifying in equal measure. It meant that the universe was vast beyond comprehension. It meant that the Earth was not at the centre of everything. And it meant that the night sky was not a map of fixed points, but a window into unending distance. But Diggis's new vision carried a strange and troubling consequence. If space was infinite, and stars filled that space in every direction, then every line of sight, no matter where you looked, should end on the surface of a star. The night sky, in that case, should blaze as bright as the sun, and yet it doesn't. The sky is dark. It was the first whisper of what would later be called Olbers' paradox. A question so simple that a child could ask it, and so deep that it would take centuries to answer. If there are endless stars, why is the night dark? That puzzle, born from a single new light in the sky, would become one of science's most elegant mysteries, and through it, humanity would slowly uncover the true size, shape, and even the beginning of the universe itself. So tonight, as you rest beneath your own quiet ceiling of stars, you're gazing at the same mystery that once lit up the imagination of Thomas Digges, a mystery that began with one impossible light and ended up revealing everything. As we drift further into the story, our path will carry us toward the next set of dreamers, the map makers of the night, who tried to draw the shape of infinity itself. Before telescopes or equations, before anyone had words like galaxy or light year, the universe was more like a story than a place. You might imagine the Earth resting still at the centre of everything, wrapped in concentric crystal spheres that turned with divine precision. Each sphere held its own treasure, one for the moon, another for the planets, and the farthest one studded with tiny lights, the fixed stars. They sparkled every night like gems pinned to the surface of a transparent dome. To the eyes of ancient observers, this made perfect sense. When you stood outside at night, the stars never seemed to change position relative to each other. They rose and set, but their constellations remained the same. So, people thought, they must all be attached to a solid shell surrounding the world, a magnificent ceiling painted with points of fire. That idea lasted for nearly 2,000 years. Aristotle taught that the heavens were perfect and unchanging. Everything beyond the moon was thought to be eternal, pure and incorruptible. Down here, things aged and broke and decayed. Up there, nothing ever died. The contrast was comforting. Earth was messy, but the cosmos above was flawless. If you could stand in an open field on a warm night long ago, you might understand why they believed this. Imagine no city lights, only the faint smell of smoke from a nearby hearth, and above you, a black canopy sprinkled with silver dust. The sky seems smooth and still, a gentle wheel turning slowly overhead. The stars don't flicker because the universe is alive. They flicker because of the air trembling above your eyes. But no one knew that then. They saw perfection, not physics. In this vision, everything had its rightful layer. The moon circled closest to us, explaining its monthly rhythm of phases. Then came Mercury and Venus, the twin messengers near the sun. Beyond them, the mighty sun itself, followed by Mars, Jupiter, and Saturn, the only planets visible to the naked eye. Each moved on its own transparent sphere, nested neatly inside the next. and beyond Saturn stretched the outermost wall of all, the firmament of stars. Beyond that wall, only heaven, not the physical kind, but the spiritual. It was an architecture that blended astronomy with faith. The firmament wasn't just structure, it was symbol. It represented the line between mortality and eternity. To cross it in imagination was to leave the human world altogether. For centuries, this model explained nearly everything people saw. It predicted eclipses, guided calendars, and provided comfort. Farmers planted by it. Sailors navigated by it. Philosophers used it as proof that nature favoured harmony. The universe was a grand clockwork, and the stars were its most elegant gears. And yet, quietly, small inconsistencies began to appear, tiny misalignments that refused to stay hidden. Planetary paths did not fit perfectly with circular motion. Some stars shimmered differently, hinting they might not all be the same distance away. Still, most scholars found ways to keep the old structure intact, adjust the math a little, add a few smaller circles, and the heavens could remain perfect. When Copernicus suggested that perhaps the Earth itself was moving, he wasn't trying to cause a revolution. He was trying to simplify the clockwork. He placed the sun at the centre, letting the planets revolve around it, yet he kept that same outer shell of fixed stars. In his mind, the stars were so far away that Earth's motion could not make them appear to shift. The sphere of stars stayed, silent and eternal. For all its boldness, even Copernicus's model didn't feel lonely. The stars still enclosed the cosmos like a beautiful wall. Humanity was no longer at the centre, but we were still safely inside something. The psychological comfort of that idea is easy to miss today. In a world of satellites and deep space images, infinity feels natural to us. But to those who lived when the world itself seemed small, the thought of endlessness was almost unbearable. A bounded universe meant order. Infinity meant the possibility of chaos. Every civilization found a poetic way to describe this cosmic boundary. The ancient Egyptians imagined the sky as the body of the goddess Nut arching over the earth. Babylonian stargazers spoke of the firmament as a river of crystal. Medieval scholars pictured angels turning the spheres with song. The specific symbols changed, but the need behind them stayed the same, the longing for a clear border between what we could see and what we could never reach. If you've ever stood on a quiet hill and watched the horizon fade, you might recognise that feeling. There's a strange peace in believing that something holds everything together, that the stars are fixed, that the universe has an edge. And yet, even as this comfort settled into culture, the sky itself was preparing to contradict it. Somewhere beyond that imagined dome, light was moving across distances no one could yet conceive. Stars were being born and dying in silence, scattering new elements into space. Entire galaxies drifted, unseen and unknown. The universe was not a tidy clock. It was already a vast, breathing ocean. But humans couldn't see that ocean yet. They needed a spark to make them question the ceiling above. That spark arrived one cold night in the late 16th century, not as theory or philosophy, but as a sudden bloom of impossible light. Across Europe, eyes turned upward to witness a brilliance that rivaled the planets themselves. It was a new star, appearing where the sky had been empty. For days it outshone every familiar constellation. People gasped, prayed, and argued. How could the heavens, supposedly unchangeable, give birth to something new? That question would reach a man named Thomas Diggers, and through him, the old crystalline sphere would begin to crack. In the glow of that strange star, the universe itself would open. If we follow the thread a little further, the story will lead us to the night a musician melted metal to mirror the heavens, and a woman counting tiny pulses of light quietly unlocked the distances between galaxies. Each of them, in their own way, will help us trade the comfort of walls for the wonder of endlessness. It began, as many turning points in science do, Not with a theory, but with a feeling, the uneasy wonder of seeing something impossible. The year was 1572. Across the cold skies of Europe, an unfamiliar light appeared. People stepped out of their homes wrapped in cloaks and looked upward in astonishment. There, in the familiar pattern of Cassiopeia, a new star blazed brighter than Venus. It shimmered through the day, outshining every planet, every star they had ever known. At first, no one knew what to make of it. Some thought it must be a comet wandering across the heavens. Others believed it was a divine message, perhaps the return of the star that once guided travellers to Bethlehem. In a time when the sky was supposed to be perfect and unchanging, this sudden new light felt like a miracle and a warning in one. Among those who couldn't look away was a curious Englishman named Thomas Diggers. He lived in a modest house in Oxfordshire and spent his nights balancing the duties of a mathematician, astronomer and translator. He wasn't searching for fame. He was searching for meaning, for the structure beneath the stars. Diggers's friend and mentor, John Dee, was a man of many fascinations, part scientist, part mystic, part advisor to Queen Elizabeth. When he and Diggers observed the strange light through their crude instruments, Dee suggested that perhaps it was a star that had wandered closer to Earth, grown brighter, and was now retreating. It was an imaginative idea, poetic, but wrong, yet it planted a seed. If a star could appear and fade, then the heavens were not perfect. They were not immutable. They could change, and therefore they could be real places, distant, physical, and alive. For years after that winter, the memory of that light stayed with Diggers. He began to wonder, if the sky could change, what else might be possible? Was the universe really a series of shells and spheres, or could it be something deeper, something without walls? In 1576, Diggers decided to publish an English translation of Copernicus's great work on the revolutions of the heavenly spheres. He admired Copernicus, who had dared to move Earth from the centre of creation to a smaller, humbler orbit around the Sun. But where Copernicus saw a finite structure, Diggers saw something far grander. He included, almost as an afterthought, a simple diagram, just circles and dots, no grand introduction. Yet that little sketch quietly became one of the most radical images in human history. On the left side of the page was Copernicus's model, the Sun in the centre, planets orbiting outward in their prescribed order, and then the final boundary, the sphere of fixed stars. Beyond that, nothing, a cosmic wall. But on the right, Diggers drew something new. He erased the wall. The stars, once bound to the firmament, were now scattered outward without end. He called it a sphere of stars fixed infinitely up. In a single gesture, he freed the cosmos. That simple act of imagination marked the first time in the Western world that anyone had described an infinite universe, a cosmos without centre, without edge, stretching forever in all directions. It was a quiet revolution, tucked between pages of translation, written by a man who didn't even own a telescope. And with that, freedom came a paradox. If the stars go on forever, then every direction we look should eventually meet one. The night sky should blaze with unbroken light, as bright as the sun itself, but it doesn't. The sky is dark. Diggers couldn't answer why. He only knew that it must mean something profound. The darkness of the night was not emptiness. It was information. It whispered that there was more to space than distance, something deeper shaping what we see. Centuries later, astronomers would give this puzzle a name, Olbers' paradox. But for Diggers, it was simply an unanswered question that would echo for generations, one that would lead, slowly, to an understanding of the true age and structure of the universe. Still, imagine the courage it took to believe in infinity in the 16th century, to believe that the stars stretched forever and that Earth was just one point adrift in that endless sea. It was as though he had pulled the curtain off the edge of existence, and instead of angels he found distance, silence, and light. The reaction from his contemporaries was a mix of fascination and unease. Some found it heretical, others dismissed it as poetic nonsense. Infinity was not comforting. It removed the boundaries that made the universe feel safe. But Digges didn't seem frightened. He found beauty in the vastness. He wrote that the stars shine perpetually, infinite in number, and no end to their brightness. He imagined that they might even host other worlds, perhaps even other beings. It was speculation centuries ahead of its time, born not from technology, but from pure thought. What Digges didn't realise was that his idea had planted a seed that would take generations to grow. In time, telescopes would show that the stars truly were suns, the nebulae would resolve into galaxies, and the sky that once seemed small would expand into a living map of billions of worlds. But for now, in the flickering candlelight of the 1500s, he was alone with his thoughts, a man staring at infinity on paper, wondering if anyone would ever see what he saw. When he looked up at the night sky, he didn't see a dome anymore. He saw a question that had no edges. And so, from that one sudden light, a star that appeared where no star should have been, came the first hint of a universe without borders, a universe that was not finished, not static, but unfolding. You can almost imagine him walking outside, the winter air cold and still, the night quiet except for the distant barking of dogs. Above him, the stars shimmer in their usual patterns, but in the heart of Cassiopeia, a strange new glow burns, fading slowly day by day. He knows he will not see its like again, yet its message has already been written into his mind. The heavens are not what they seem. If we let our thoughts drift a little further along this thread, the story begins to widen. The centuries ahead will bring new eyes, new mirrors, and new ways to measure distance itself. The stars that Digges scattered across his infinite page will soon become points in a real charted sea. And the next dreamer to pick up where he left off will not be a philosopher, but a craftsman, one who built mirrors to catch the light of heaven and tried to draw the shape of everything. When Thomas Digges scattered the stars across infinity, he didn't just redraw the sky, he rewrote the human imagination. For thousands of years, the universe had felt contained, almost domestic, like a great cathedral built to scale around the earth. Now, suddenly there were no walls, the floor was gone, the roof was gone. Humanity found itself standing in open space for the first time. It was a beautiful thought, and also a frightening one. Infinity has a way of stealing sleep from even the calmest minds. The idea that the universe could stretch on forever, filled with endless stars, made the world feel both grand and unbearably small. Where then was the centre? Where was heaven? Where was safety? Digges, for his part, saw wonder in the vastness. He wrote that the fixed stars are infinite in number, and every one a world like ours. He imagined a cosmos where creation was not confined to one corner, but scattered like seeds across boundless soil. It was perhaps the first whisper of what we now call the cosmic principle, the idea that no place in the universe is truly special. Every part of space, in its own quiet way, belongs to the same grand design. But if space was truly endless, another question lingered in the shadows, one that Digges couldn't answer. If there are infinite stars filling every corner of space, then why is the night sky dark? It's a question so simple that even a child might ask it, yet so deep that it puzzled scientists for centuries. Imagine an infinite forest, with trees in every direction. No matter where you look, your gaze should eventually meet a trunk. In the same way, if the universe is infinite and evenly filled with stars, every line of sight should end on a star's glowing surface. The entire sky should blaze with light, and yet it doesn't. The night sky is black, punctuated by a few bright points that seem almost fragile against the dark. The stars, no matter how many there are, do not overwhelm us. They shimmer quietly in a sea of nothing. This mystery, later called Olber's paradox, would become a key to unlocking the structure of the cosmos. But in Diggis's time, it was simply a contradiction too large to solve. The universe was infinite, and yet not bright. Somewhere, something didn't fit. Philosophers tried to reason with it. Some suggested that cosmic dust might block the light of distant stars, as if the universe were a vast fog. Others thought perhaps the stars burned out faster than their light could fill the sky. But none of those explanations truly satisfied the deeper question. If the universe has existed forever, then its light should already have reached us from every direction. To understand why it hasn't, humanity would first need to understand distance itself, and time, and how light moves through both. But that understanding lay centuries ahead, waiting for the invention of telescopes, mirrors, and mathematics powerful enough to measure the unmeasurable. Still, Diggis had unknowingly set the stage. He had opened the curtain to infinity, and behind it lay the dark mystery that would eventually lead to the discovery of the expanding universe, the beginning of time, and the faint microwave echo of the Big Bang. But that is getting ahead of ourselves. For now, imagine the world as it was in the late 16th century. Europe alive with new maps and new ideas. Sailors crossed oceans, charting coastlines no one had ever seen. Artists painted perspective into flat images, learning how distance could be made visible. And in the same spirit, astronomers began trying to chart the heavens. The sky became another map to be drawn, not symbolic or sacred, but measurable. The stars, once divine jewels, became data points. Humanity had taken its first step from mythology into astronomy. Still, Diggis and his contemporaries had no way to measure how far away the stars really were. To them, infinity was not a number, but a feeling, a sense of endlessness that could only be imagined, not quantified. They could see that the stars were not fixed to a shell, but they couldn't yet prove that they were scattered across true depth. The scale of the universe was, for now, invisible. But the idea of measuring it would soon begin to take shape in unexpected places, in the hands of craftsmen polishing metal mirrors, in the quiet patience of those who stared through telescopes night after night, counting the faint points of light. Looking back, it's hard not to admire the courage of those early thinkers. They stood at the edge of everything they knew and dared to say, this might not be all. The universe they described was not yet correct, but it was reaching in the right direction, outward. And even though Diggis couldn't explain why the night was dark, his question never went away. It lingered in the work of later astronomers, who would slowly realise that the darkness itself was a clue, a quiet proof that the universe was not eternal and static, but young and changing. Much later, we would learn that light travels at a finite speed, about 300,000 kilometers per second, and that the stars we see tonight are not where they are now, but where they once were. Some of them may no longer exist at all. Their light is a message sent long ago, still crossing the gulf of time to reach our eyes. But in the 16th century, such thoughts were beyond imagination. For Diggis, the darkness was not yet a mystery to solve. It was simply a canvas for wonder, and perhaps that was enough. Science often begins not with certainty, but with awe. Diggis's infinite universe was wrong in details, but right in spirit. He had replaced perfection with possibility. So when you step outside and see the night sky, the same sky that Diggis once looked upon, you're not just seeing stars, you're looking at the question that opened the modern age. Why is it dark? It's a question that has followed us for 4 centuries, whispering through telescopes and satellites and equations, until finally we began to understand that the darkness is not the absence of light. It is the shadow of time itself. As we drift further into the story, our quiet exploration now turns toward those who tried to measure this infinite night. the patient stargazers who built mirrors to catch the faintest rays, hoping to draw the shape of everything. From the sparks in their workshops to the gleam of a telescope under the stars, they would begin the long, delicate work of turning infinity into a map. In the small English town of Bath, late in the 18th century, the night often echoed with the faint clatter of metal, the hiss of a furnace, and the quiet voices of two siblings working through the dark. Their names were William and Caroline Herschel, a brother and sister who, without intending to, would open the heavens wider than anyone before them. William had come to England from Hanover, Germany, not as a scientist but as a musician. He played the oboe, conducted orchestras and taught lessons by day. Yet something in him always tilted toward the sky. After his performances, he would walk home through the sleeping streets, look up at the stars and wonder what kind of pattern might hold them all together. It began modestly, a curiosity, a hobby, a way to pass quiet hours. But curiosity has a way of expanding, like light through glass. William soon grew frustrated with the small telescopes he could afford. They were cloudy, faint, unable to show him what he felt was really out there. So, with the precision of a musician tuning an instrument, he decided to build a better one himself. His sister Caroline helped. In a cramped back room behind their house, they melted metal in a small furnace. The air shimmered with heat. Sparks jumped like tiny orange fireflies, leaving dark specks on the stone floor. Together they mixed copper and tin, trying to find the perfect balance. Not too brittle, not too soft, to make a mirror that could drink starlight without distortion. There were no safety gloves, no ventilation, no machines to smooth the surfaces. William poured the glowing liquid metal into a circular mould, then cooled it slowly. Once solid, he and Caroline began the most patient part, grinding and polishing. For hours, sometimes for days, they moved the metal in small, deliberate circles, their shoulders aching, their hands sore, until the surface was so perfect that a candle flame could reflect in it without trembling. That mirror, that hand-polished disc of metal, became the heart of their first great telescope. It wasn't made of glass, but of gleaming bronze, curved so precisely that it gathered even the faintest rays from distant stars and bent them toward the human eye. Herschel called these instruments specula, mirrors that could speculate, or think, with light. When William finally pointed one toward the sky, the world he saw changed forever. The stars no longer looked like scattered decorations on a black dome. They had depth. They were not painted on a ceiling. They floated in layers, stretching away into unfathomable distance. The firmament had dissolved. The sky was an ocean. Night after night, Caroline stood beside him, taking notes as he called out his observations. She organised them, checked the times, and catalogued thousands of stars. While William scanned the heavens, Caroline swept the near sky for comets. She would eventually discover 8 of them, small icy wanderers glowing faintly in the dark. But their greatest discovery came by accident. One night in 1781, while studying a familiar patch of stars, William noticed a faint disk that seemed to move against the background. It wasn't a star, nor a comet, nor anything in his catalogue. After careful observation, he realised it was something completely new, a planet. He had found Uranus, the first new planet discovered since ancient times. News of the discovery travelled fast. King George III appointed him royal astronomer, giving him the time and support to pursue his passion full-time. But Herschel's true obsession was not with individual planets or stars. It was with the shape of the whole sky. He wanted to map it, all of it. Imagine that for a moment. One man and his sister, with hand-built instruments, attempting to chart the structure of the universe. Each night, they divided the heavens into narrow slices, moving the telescope inch by inch, counting and recording every star that appeared in its view. It was tedious, exhausting work. Yet from that devotion came something extraordinary. In 1785, Herschel produced a map that revealed for the first time the outline of our Milky Way. It wasn't a perfect drawing, it was a rough sketch, uneven, human, but it showed a vast disc-shaped collection of stars with a brighter core in the middle. At its centre, he placed our sun, thinking he had found the balance point of creation. He believed he was looking to the very edge of everything. What he didn't yet know was that his map was like a pebble placed near the shore of an endless sea. He had seen a boundary, yes, but it was only the edge of our own galaxy, not the universe itself. Still, it was the first time anyone had tried to give the cosmos a shape. Caroline's quiet labour made much of this possible. She once wrote, almost apologetically, that she was a tool in the hands of the great artist. But in truth, she was the heartbeat of their discoveries. When William's health declined, she continued to organise, to measure, to refine their data. Years later, the Royal Astronomical Society would honour her in her own right, the first woman to receive such recognition. Their work changed astronomy from philosophy into craft. The stars were no longer unreachable symbols. They became measurable, countable, physical, each one a piece of the universe's architecture. Yet even as Herschel's telescopes pierced deeper into the sky, new mysteries appeared. Through his larger instruments, he began to notice faint cloudy patches, strange smudges of light that didn't behave like stars at all. Some looked round, some spiraled, some diffuse and ghostly. Were these clouds within our Milky Way? Or were they something else entirely? Vast collections of stars far beyond? Herschel didn't know. His mirrors were powerful, but the universe was deeper still. The answers were hidden behind the limits of light itself. For now, he could only note their presence, give them numbers, and move on. Even in his later years, Herschel wrote that he often wondered what lay beyond those clouds. "When I look into the heavens," he said, "I see the construction of worlds, and I feel myself almost lost." It's a sentiment we still understand. To look up at the night sky is to feel both infinite and small, to be humbled by the scale of existence, yet comforted by the thought that our eyes can reach it, even a little. As we drift further into the story, we follow the faint trail left by those ghostly clouds, the nebulae that Herschel could only guess at. Others would later take up his question, searching for a way to measure what cannot be touched, the true distances between the stars. Their tools would be subtler, their patience quieter, but their dreams just as vast. By the end of the 18th century, the night sky had begun to feel a little larger, a little more uncertain. William Herschel's telescopes had pulled the stars closer, revealing the Milky Way not as a ceiling, but as a great luminous river made of countless suns. Yet among those countless points of light, he kept noticing something different. Faint, smoky patches that refused to behave like stars. They weren't sharp or steady. They didn't twinkle. They hovered in his eyepiece like breaths of mist. He called them nebulae, a word that simply meant clouds. Some were round, some spiral, some looked like smudges brushed onto the darkness. Caroline helped him catalogue hundreds of them, carefully sketching their shapes and marking their positions. Each night, as William counted stars, she traced the delicate ghosts between them. But what were they? No one knew. Were these glowing patches made of gas and dust within our own galaxy? Or were they entire systems of stars too distant to resolve? Island universes as some dared to imagine? For Herschel, the question was tantalizing but unreachable. His telescopes could see farther than any built before, but even their polished metal mirrors had limits. The deeper he looked, the more the universe seemed to retreat, like a horizon always just beyond reach. Still, he tried to make sense of it. To him, the nebulae might be cosmic nurseries, places where new stars were being born. Or perhaps they were the remains of old suns that had burned out, their ashes scattered through space. The truth, he thought, might lie somewhere in between. He began to suspect that the universe might not be uniform at all. Maybe it had texture, structure, clusters of stars, families of galaxies, and that what he saw through the eyepiece were glimpses of that structure. The heavens, he wrote, are a boundless ocean of suns. But beyond that ocean, even his instruments went blind. It's strange to imagine now, in an age of satellites and space telescopes, that there was a time when no one knew what a galaxy was. The Milky Way was thought to be the entire universe, everything that existed. To think that there could be others, each containing billions of stars, was almost unthinkable. And yet, hints of that vastness kept appearing in those cloudy patches. In one, Herschel saw a spiral form, like a whirlpool frozen in light. In another, a soft halo surrounding a brighter core. He made sketches that still survive, small pencil drawings filled with wonder. Each line on the paper was a guess about the shape of reality. As technology advanced, astronomers began to dream of measuring how far away those nebulous clouds truly were. But distance, in astronomy, is a fragile thing. How do you measure something when you can't approach it? How do you reach across light years with only your eyes? The first clue came not from a grand observatory, but from a simple act of noticing. The way nearby stars seem to shift ever so slightly as the Earth moves around the Sun. It's a trick of perspective, something you can try yourself. Hold your finger in front of your face and close one eye, then the other. You'll see your finger appear to jump back and forth against the background. That small motion is called parallax. Astronomers realized they could use the same principle to measure the distances to the nearest stars. As Earth traveled along its orbit, the stars should appear to wobble ever so slightly against the far background. By measuring that tiny shift, one could calculate how far away a star truly was. But the angles involved were unimaginably small. Far too small for Herschel's instruments. It would take another generation and another level of precision before anyone could detect such a movement. In the early 1800s, a German astronomer named Friedrich Bessel decided to try. Using an instrument called a heliometer, essentially two telescopes combined into one, he observed a faint star named 61 Cygni. For months he compared its position against neighbouring stars, recording the tiniest changes he could detect. What he found was astonishing. The star's apparent motion across the sky was so small it could barely be measured, yet it was real. By his calculations, the star was around 100 trillion kilometres away. That distance is impossible to visualise, so think of it like this. If light itself, the fastest thing in the universe, were to leave that star and travel toward us, it would take nearly 11 years to arrive. And yet, even this immense gulf was just the beginning. Herschel's nebulae lay far, far beyond. The parallax method, brilliant as it was, could only reach the nearest neighbours, the stars next door. Everything beyond that remained hidden behind a curtain of immeasurable distance. For astronomers of the 19th century, it was both exhilarating and maddening. They could sense the immensity of the cosmos, but they couldn't yet map it. They had rulers too short for the task. Some began to wonder if the nebulae were clues, if the universe contained structures on scales no one had yet imagined. Others argued that the patches were simply gases within our own galaxy. The debate would grow heated, stretching into the next century. For now, the nebulae hovered between definitions, waiting for better eyes. But even with those limits, Herschel and his successors had accomplished something profound. They had replaced the myth of a perfect, unchanging sky with the image of a dynamic, layered universe, one that grew deeper the longer you looked at it. It's humbling to think that centuries later we still use Herschel's method of mapping, looking, counting, comparing and wondering. We build machines of glass and steel instead of metal and hand-ground mirrors, but the essence is the same, a human gaze reaching outward, trying to measure the unmeasurable. If you step outside on a clear night, and find the faint blur of the Andromeda Galaxy, just visible to the naked eye as a small misty patch, you'll see something Herschel could only dream of understanding. That blur is not a cloud at all, but another Milky Way, filled with stars that have been shining for billions of years, and the light that touches your eyes tonight began its journey long before humans existed. It has crossed vast stretches of time and space, a quiet traveller from another world, arriving just now to be noticed. As we drift further into the story, our trail of curiosity leads us into a quieter world, one without roaring furnaces or glowing metal, but filled with patience and light. It is the story of a woman who measured not through strength, but through rhythm, who discovered that the distance to the stars could be found not by reaching outward, but by listening carefully to their pulse. By the early 20th century, the great telescopes of the world had grown larger, their lenses clearer, their mirrors brighter. But the question of distance, how far the stars and nebulae truly were, still haunted astronomy like a half-finished melody. The night sky shimmered with billions of suns, yet no one could say how far that light had travelled to reach us. Humanity could see the orchestra of stars, but not the music of their spacing. The person who would quietly begin to solve this puzzle worked not beneath a telescope dome, but in a small room filled with glass plates and silence. Her name was Henrietta Leavitt, and she worked at the Harvard College Observatory at the dawn of the 20th century. The observatory's walls were lined with shelves of photographic plates, thin sheets of glass coated in silver salts, each capturing a frozen field of stars. Day after day, Henrietta and a group of women known as the Harvard Computers examined these plates by hand, using magnifying lenses and simple rulers. They weren't allowed to use the observatory's telescopes. Their task was considered clerical: to measure, to classify, to catalogue. But hidden in that repetition, Henrietta saw something extraordinary. She spent her hours studying stars that seemed to blink, their brightness waxing and waning in steady rhythm. These were known as Cepheid variables, stars whose light pulses with a regular beat like the slow breathing of a cosmic heart. On the plates, Henrietta marked each one with tiny dots of ink, recording how its brightness changed from image to image. After months of study, she began to notice a pattern. The brighter a Cepheid was, the longer its pulse took to complete. In other words, there was a strict relationship between a star's true brightness and the length of its rhythmic cycle. A Cepheid that blinked quickly was dim and close. One that blinked slowly was bright and far. It was as if the stars were whispering their distances through time. This discovery might sound abstract, but it was quietly revolutionary. Imagine standing on a dark shoreline, seeing distant lighthouses flicker along the coast. If you knew how bright each lighthouse truly was, you could tell how far away it must be by how dim it appears. Henrietta had found a universal rule, a way to turn brightness into distance. She had, without realizing it, built a cosmic yardstick, one that could reach far beyond the limits of parallax. The relationship she uncovered would later be called the period luminosity law. But there were no equations on her page, no elaborate instruments, just columns of numbers and her delicate handwriting, the quiet heartbeat of discovery written in pencil. For centuries, astronomers had dreamed of finding a way to measure the unreachable, and here it was, discovered by a woman working in a quiet corner, denied access to the very telescope whose images she interpreted. Henrietta never sought fame. She didn't know that her insight would one day reshape humanity's view of the universe. She simply continued her work, measuring more stars, checking her results, making sure the rhythm held true. And it did. Every blinking Cepheid obeyed the same pattern. Later, astronomers would test and refine her findings, but the core idea remained untouched. The universe has its own rhythm, and by listening carefully we can measure its scale. Henrietta once wrote that her work gave her a feeling of deep connection, as if the stars had voices and I was allowed to hear their conversation. It's a beautiful thought, that amid all the data and precision, science can still feel like listening. Her discovery bridged the gap between imagination and measurement. It gave astronomers a ladder to climb from the nearby stars to the distant nebulae that Herschel had seen as mysterious clouds. For the first time, humanity had a way to test whether those smudges of light were within our galaxy or far beyond. But recognition came slowly. In her lifetime, Henrietta received little credit for her work. Her health declined, and she died before seeing how her discovery transformed astronomy. Yet, decades later, her method would become the foundation for one of the greatest revelations in science: the proof that our Milky Way is just one of many galaxies scattered across the vast dark. There is a quiet poetry in that. A woman who never touched a telescope gave us a way to measure the unreachable. She turned the stars flickering into meaning, the pulse of light into cosmic distance. If you picture her sitting at her desk, surrounded by glass plates that shimmer faintly in the lamplight, you can almost feel the rhythm she discovered. Each star blinking gently, marking its time. Short, long, an endless code written in the darkness. And in that rhythm, she heard not just numbers, but music. The stars were keeping time, and she was their patient listener. It's hard not to think of the irony. While the great observatories built ever larger domes, the secret to their distances was uncovered in silence by someone who worked quietly in the margins of the night. Yet this is how discovery often happens, not through thunder, but through stillness. The universe reveals its truths to those who are willing to listen closely, to notice patterns that others overlook. Henrietta's work reminds us that science, at its best, is not only about instruments or equations, but about attention, the kind of deep, gentle noticing that turns repetition into revelation. Her law, simple and elegant, gave the next generation of astronomers the tool they needed to measure the universe itself. One of them would be a man named Edwin Hubble, a restless observer who would look through a massive telescope high above Los Angeles and realize that those faint nebulae Herschel once saw were not clouds at all, but galaxies, each one a world of stars beyond our own. In that moment, Henrietta's quiet discovery would become the key that unlocked the scale of everything. If we follow the thread a little further, we'll climb with Hubble up the mountain, into the thin air above the city's glow, and peer through the great Hooker telescope. There, in a small patch of sky, he would find a single blinking star, and with it, the first proof that the universe is far larger than anyone had ever dreamed. The mountain was quiet except for the wind. High above the haze of Los Angeles, in the thin, cold air of Mount Wilson, a great dome of silver steel turned slowly against the stars. Inside it, a young astronomer adjusted the levers of a machine so massive it groaned when it moved. The telescope before him was the largest of its time, a mechanical cathedral for light. His name was Edwin Hubble, and his nights were spent chasing the faintest glimmers at the edge of sight. The year was 1923, and through that giant instrument, the Hooker telescope, he was peering into what was then known as the Andromeda Nebula, a faint spiral of light just visible to the naked eye on clear nights. For centuries, astronomers had puzzled over these hazy spirals. Were they small clouds of gas within our own galaxy, or entire star systems far beyond? The question was known as the Great Debate, and it split astronomy in two. Some believed that the Milky Way was the entire universe. Others whispered that the universe might contain countless Milky Ways. Hubble, restless and meticulous, decided to settle the matter. Using photographic plates, large sheets of glass coated with light-sensitive chemicals, he captured Andromeda again and again, each exposure lasting for hours. He studied the results under a microscope, scanning for stars that seemed to flicker or pulse. Night after night, he searched for a pattern, for something familiar. And then, one evening, he saw it. A single, tiny dot that changed brightness between exposures, blinking like a heartbeat frozen in time. He realized what he was looking at. It was a Cepheid variable, one of Henrietta Leavitt's rhythmic stars. Excited, Hubble marked the glass plate with a small note beside the star. Just 3 letters. VAR, short for variable. It was a quiet exclamation, a scientist's way of shouting across time. Using Leavitt's discovery, her law linking a Cepheid's rhythm to its true brightness, Hubble could now estimate how far away that star must be. And when he did the calculation, the answer left him breathless. The star, and therefore the whole Andromeda spiral, was far outside the boundaries of our Milky Way. Not just a little beyond, but millions of light years away. To put that in perspective, imagine light travelling from that star as if it were a messenger running across the universe. It would have started its journey long before humans walked the Earth, crossing the emptiness for more than 2 million years before finally arriving on that fragile piece of glass in Hubble's hands. This was the moment the universe changed size. Until that night, our galaxy had been the whole of existence, a single island of stars floating in darkness. But with one blinking dot, that illusion shattered. Andromeda was not a small cloud inside our galaxy. It was another galaxy entirely, a vast collection of billions of stars, a distant city of suns. The cosmos had expanded 1,000,000-fold in the human mind. Hubble later wrote that when he saw the variable star on the plate, he felt as though a door had opened onto infinity. The distances were beyond comprehension, and yet somehow measurable. A universe of galaxies, each one separated by unthinkable gulfs of space, each perhaps with its own planets, its own moons, its own forms of light and silence. The news travelled quickly. Within a year, astronomy had a new map of reality. The Milky Way was no longer the universe. It was merely one among billions of others. The word galaxy itself took on a new meaning. Not just our home, but one of countless homes in the endless dark. In time, Hubble's discovery would lead to an even greater revelation, that the universe was not static, but expanding, stretching like a living fabric. But in 1923, that idea still lay beyond the horizon. For now, the shock of scale was enough. Humanity had peered beyond the walls of its cosmic village and found an entire ocean. It's worth remembering that this revolution began with patience, with the rhythm of Leavitt stars and the delicate mark of a pencil on glass. 2 people separated by decades and circumstance, their work joined in light. One listening to the pulse of the stars, the other watching that pulse echo across galaxies. Together they bridged the unimaginable. Hubble himself was a curious blend of explorer and showman. He wore tailored suits to the observatory, quoting Shakespeare while adjusting his instruments. Yet beneath the flair was genuine reverence. In the stillness of the dome, he treated each exposure as an act of devotion. The universe, through his telescope, was no longer a distant dream. It was a living, expanding reality full of motion and time. If you could stand beside him on one of those nights, you would see the telescope glide slowly across the sky, following Andromeda's ghostly light. You'd hear the faint hum of machinery, the scratch of pencil on paper, and the quiet whisper of wind brushing against the dome. Far below, the city of Los Angeles glowed faintly, its lights twinkling like a second artificial constellation. But up here, in the chill and silence, another kind of light was being gathered. Light that had travelled longer than any story, crossing eternity to tell us where we are. Today, when you look at Andromeda through binoculars or a camera lens, you are seeing the same faint spiral that Herschel once catalogued as a cloud, the same smudge that puzzled centuries of stargazers. But you're also seeing Hubble's revelation that this is not just a mist, but an entire galaxy, the nearest great neighbour to our own. Every photon that enters your eye began its journey 2.5 million years ago, long before there were cities or songs, crossing the abyss in perfect silence. And now, at the end of that journey, it touches you, a brief, golden arrival after an eternity of travel. When Hubble realised this, he wrote that, "The history of astronomy is a history of receding horizons. The farther we look, the more there is to see. The more we measure, the larger the unknown becomes. And perhaps that's the quiet beauty of it, that the sky will never be finished, that the act of looking itself is infinite." As we drift further into the story, the path now carries us away from glass and steel into something stranger, the invisible architecture that holds it all together. We've seen how light can reveal distance, but soon we'll explore how space itself can bend, stretch, and shape the stars. Our quiet journey now turns toward the hidden geometry of the universe, and to the mind that first realised that even nothing can curve. After the great discoveries of distance, after Herschel's mirrors and Leavitt's rhythms and Hubble's galaxies, one question still hung in the dark like a quiet echo. What is all of this inside of? When we speak of the universe expanding, of galaxies drifting apart like islands on a rising tide, we tend to imagine them floating in something, perhaps a great invisible sea, or a void, or a black backdrop dotted with stars. But what is that backdrop made of? What exactly do we mean when we say space? For most of human history, space seemed obvious. It was the room in which things existed, a box that held the stars, the planets, and us. When you walk into an empty room, you can sense the space around you. It has volume, distance, openness. So it felt natural to think of the universe in the same way. A giant room, vast beyond measure, but still a container of things. The first to turn that feeling into structure was a man named Euclid, more than 2,000 years ago. He was a mathematician, but his work had the rhythm of poetry, simple statements about points, lines, and shapes that became the foundation of geometry. In Euclid's world, space was flat and logical. Two parallel lines, he said, will never meet. The shortest distance between 2 points is a straight line, and the angles of a triangle always add up to 180 degrees. These rules became so natural that for centuries no one thought to question them. They simply described the world as it appeared, orderly, consistent, comforting. You can see Euclid's logic everywhere, in the walls of buildings, in the lines of roads, in the predictable arc of a bridge. The geometry of daily life feels solid, and for millennia people believed the same was true of the cosmos. The stars were fixed in their precise locations because the universe itself was built on unbending rules. But as telescopes improved and the stars revealed their restless movement, some began to wonder whether space was really so simple. Could it be that what looked straight was not truly straight, but only appeared so because we were too small to notice its curve? Imagine holding a small piece of paper and looking at its flat surface. To you, it seems perfectly level. But now imagine that you are an ant walking across it. If the paper were wrapped into a gentle curve, you might not feel that curvature at all. You'd still think you were walking in a straight line, even though, from above, an observer could see that your path bends. The same might be true, some began to suspect, of the universe itself. The first to glimpse this possibility was Carl Friedrich Gauss, a quiet genius born in Germany in the late 18th century. He was fascinated by patterns, in numbers, in stars, in the shape of the Earth itself. He realised that even without stepping outside a surface, you could determine if it was curved. Imagine our tiny ant again, walking across a globe. If it draws a triangle from the North Pole down to the equator, walks along the equator, and returns to the pole, it will discover something strange. The sum of the triangle's angles will be greater than 180 degrees. That difference is proof of curvature, visible from within, without ever having to see the sphere from the outside. This realization changed everything. Space might not be flat after all. It might have shape. Others followed Gauss's trail, including his brilliant student Bernhard Riemann, who extended the idea further. Riemann wondered if not just surfaces, but the space itself, the three-dimensional volume we live in, could also curve. Could the geometry of the universe bend and stretch like fabric, not just in 2 dimensions, but in 3, or even 4? He imagined that the rules of distance might change depending on where you were. 2 lines that seemed parallel might eventually meet. A beam of light might curve without anything pulling on it. The universe, he said, could be a kind of flexible stage, one that shapes itself to the matter it contains. At the time, these were just mathematical dreams, too abstract for most to take seriously. But they lingered, waiting for someone who could turn them into a description of reality. That person would come in the early 20th century, a century after Riemann, with a gentle face and wild hair, a man whose thoughts would bend the world. His name, of course, was Albert Einstein. Before Einstein, people thought of space as a quiet emptiness, a stage where events played out but never changed itself. Time, too, was considered separate and steady, ticking forward like a metronome no matter what happened. But Einstein saw something different. He realized that space and time are not separate at all, but woven together into a single fabric, space-time, and that fabric is not rigid. It bends and curves in response to mass and energy. In simpler words, the presence of matter tells space how to curve, and the curvature of space tells matter how to move. It's a sentence that sounds like poetry more than physics, and that's how it should be read. Instead of thinking of gravity as an invisible pull, Einstein imagined it as the shape of the path that everything naturally follows. To picture it, imagine stretching a soft blanket and placing a heavy ball in the middle. The fabric dips. Now, if you roll a smaller ball nearby, it doesn't fall toward the big one because of a mysterious force. It follows the curve in the fabric. The ball moves where space tells it to go. That's gravity. Not as a tug from afar, but as a quiet conversation between matter and the geometry of space itself. Einstein's insight turned the universe into something alive, not a static arena, but a dynamic entity that bends, twists, and even vibrates. He took the calm, flat geometry of Euclid and breathed motion into it. Suddenly, emptiness wasn't empty anymore. It had structure, flexibility, and depth. The void could ripple, and nothingness itself could have form. This idea would soon explain everything from the orbit of Mercury to the bending of light around stars. It would also, unexpectedly, lead us to one of the greatest surprises of all, that the universe itself is expanding. But for now, in this quiet moment of discovery, what matters most is the realization that space is not just where things are. It's part of what things are. Every atom, every star, every galaxy shapes the fabric it inhabits, and that fabric in turn shapes their dance. We do not move through space, we move with it. As we follow the thread a little further, our story carries us into that next idea, the proof that even vast nothingness can bend and breathe. The path now leads us gently to the mind of Gauss's student Riemann, and to the elegant mathematics that gave Einstein the language to describe the curvature of the universe itself. By the time Carl Friedrich Gauss was born, the world had already begun to stretch beyond its old boundaries. The sky was no longer a ceiling. The Earth itself was being mapped, measured, and understood with astonishing precision. Yet Gauss saw something that others didn't. He looked at maps, triangles, and the delicate geometry of the world and wondered, what if the space beneath our feet wasn't perfectly flat at all? Gauss had been a mathematical prodigy, but his genius wasn't loud. It moved quietly like the curve of a river, gentle at first glance but powerful underneath. He was fascinated by patterns, the way numbers seemed to hum with hidden structure. As a child, he once amazed his teachers by adding all the numbers from 1 to 100 in a few heartbeats, finding symmetry in what looked like chaos. But it was geometry that truly caught his imagination, because geometry seemed to whisper something about the shape of reality itself. For 2,000 years, people had trusted the geometry of Euclid: straight lines, right angles, and certainty. In Euclid's world, the rules were simple. Parallel lines never meet. Triangles always add up to 180 degrees. It was a geometry so perfect that it became almost sacred. Cathedrals, bridges, and even philosophy were built upon it. But Gauss began to notice that nature didn't always obey these clean rules. Mountains curved the horizon. The Earth itself, when measured carefully, didn't fit the perfect proportions of a sphere or a plane. The more precisely you measured, the more reality seemed to bend. He realized that if you drew a triangle on the surface of a globe, say one point at the North Pole and two on the equator, the sum of its angles would be greater than 180 degrees. Something invisible, yet undeniable, was shaping those lines. Gauss began to suspect that curvature was not an illusion, it was a property of the world itself. What made this insight extraordinary was that he didn't imagine it from outside, looking down on the Earth like a god with a ruler. He imagined it from within. He wanted to know, could a being who lived entirely on a curved surface tell that it was curved without ever stepping off it? To answer that, Gauss invented a remarkable idea, what he called the intrinsic curvature of a surface. It meant that you could measure curvature from the inside without any reference to an outside world. You could, in principle, be an ant on a balloon and still prove that the balloon was curved, even if you could never see the balloon itself. It was a quiet revolution. Geometry, it turned out, didn't need the safety of flatness. The universe could curve, twist, and warp, and the rules could adapt. Gauss himself applied these ideas to the real Earth. As a surveyor, he helped create one of the most precise maps of Germany ever made. He used the stars to triangulate mountains, measuring the smallest differences in angle. His data surprisingly hinted that the large-scale shape of the Earth's surface was ever so slightly non-Euclidean, not perfectly flat, not perfectly round. Reality was flexible, like a living surface. You might imagine Gauss sitting in the open countryside, his instruments gleaming in the sunlight, a quiet smile on his face as he compared his numbers. To everyone else, it was cartography. To him, it was revelation. He was seeing the first trace of a curved universe. He once wrote to a colleague that he had discovered beautiful truths, but he dared not publish them. The world, he feared, was not ready. The idea that space itself could bend was too radical. In an age still haunted by the ghost of perfect geometry, Gauss kept his discovery close to his chest, sharing it only with a few trusted friends. One of them was a young mathematician named Bernhard Riemann. Riemann studied under a Gauss, and when he first read his mentor's notes, he was struck by the quiet audacity of the idea. To him, it was as though Gauss had pulled a single thread, and behind it, an entirely new tapestry was waiting to unfold. If two-dimensional surfaces could curve, Riemann reasoned, why not three-dimensional space? Why not the entire universe? Gauss had given him a way to measure curvature from within, and Riemann would take that idea into the unimaginable, building a new kind of geometry where lines could meet, space could twist, and parallel paths might one day converge. But that would come later. For Gauss, the discovery remained something intimate, almost secret. He didn't need the world's applause. He was content knowing that he had touched a hidden structure that few had ever imagined. The story of Gauss's hidden curvature is not just about numbers, it's about perspective, the shift from looking at space to living in it. It's about realizing that the ground beneath us, the air above us, and the stars around us might not obey the flat, perfect lines we once thought they did. And perhaps it's a story about humility. Because once you accept that space can bend, you also have to accept that what seems straight to you might not be straight at all. Your sense of order might simply be a matter of scale. Gauss once described mathematics as the queen of the sciences, but the kind of math he practiced was closer to art, full of intuition, pattern, and mystery. His work opened a doorway that would eventually lead Einstein to his theory of relativity, though Gauss himself never lived to see that connection. What he did leave behind was a quiet understanding that the universe does not have to be flat to make sense. Its beauty lies not in rigidity, but in flexibility. The stars we see might not be dots scattered across a perfect dome. They might be arranged along gentle curves, tracing the contours of an unseen fabric. If you ever stand on a hill and watch the horizon bend away from you, or trace the arc of the moon rising through thin clouds, you are seeing what Gauss felt, the elegance of curvature hiding in plain sight. In his old age, Gauss often worked late into the night by the light of a single candle. He once said that the joy of discovery was like finding a key in the dark and realizing it fits a lock you never knew existed. His key would one day unlock the structure of the cosmos itself. As we drift further into the story, we follow the faint glow of that candle toward the student who dared to imagine even more, Bernhard Riemann. He would take Gauss's secret insight and give it wings, extending it beyond surfaces into the very fabric of the universe. And from his ideas, Einstein would later draw the language to describe how gravity itself is simply space learning to curve. Bernhard Riemann was a quiet man with a mind that stretched far beyond the horizon of his age. To those who met him, he seemed shy, almost fragile, a scholar who hesitated to speak, but whose thoughts, when they did emerge, could bend the world. He was born in Germany in 1826, the son of a poor pastor, and grew up surrounded by forests, rivers, and books that were often borrowed rather than owned. But from the beginning he seemed to live partly in another dimension, not the visible world, but a world of patterns and possibilities. Riemann's fascination with space began where Gauss left off. He had studied under the great man at Göttingen University, absorbing his ideas about curvature and geometry that could be measured from within. To Riemann, those ideas were not just mathematics, they were poetry written in numbers. They whispered that the universe might be more flexible, more imaginative than anyone had dared to believe. For centuries, the geometry of Euclid had felt like solid ground. It described the world we could see, flat surfaces, straight lines, perfect circles. But Riemann sensed that this was only a small corner of a much larger landscape. What if there were other kinds of space? Spaces that bent not just in 2 dimensions, like the surface of a globe, but in 3 or even 4. In the summer of 1854, at the age of 28, he was invited to give a lecture that would change the history of science. The title was simple, but the ideas within it were anything but. He called it "On the Hypotheses Which Lie at the Foundations of Geometry." Standing before an audience of scholars, Riemann spoke softly, almost nervously. But as he described his vision, a strange beauty filled the room. He explained that the rules of geometry, those old, dependable truths about triangles and straight lines, might not be universal. They might simply describe one possible version of space. In others, lines that seemed parallel could eventually meet. In others still, a triangle's angles might add to more than 180 degrees, or less. To explain the idea, Riemann used an image simple enough for anyone to imagine. He said, "Think of a sheet of paper, flat, smooth, familiar. Now imagine bending that paper into a curve. On that surface, the rules begin to change. Distances warp. Lines that once seemed straight begin to meet. But then, he added something breathtaking. What if space itself could be curved in this way? Not just a surface, but the very 3-dimensional stage we live in. What if the universe has no outside, no boundary, no edge, because it curves back upon itself in dimensions we cannot see? It was the birth of a new geometry, one that could describe worlds beyond human perception. Riemann proposed that every point in space could carry its own rulebook for measuring distance, a kind of built-in compass that changed subtly from place to place. The universe, in his view, was not a fixed grid, but a living fabric, flexible and responsive, its shape defined by what it contained. He couldn't have known it then, but this vision would one day become the foundation of Einstein's general theory of relativity, the mathematical language of curved space-time. At the time, however, Riemann's ideas were so abstract that most of his audience couldn't fully grasp them. Even Gauss, who had quietly anticipated some of these thoughts, was astonished. He called Riemann's lecture a piece of work of the highest originality. Riemann continued to refine his ideas, introducing what he called a manifold, a way to describe spaces of any number of dimensions. It's a word that sounds complicated, but the idea is simple if you imagine it. A manifold is just a landscape whose shape can change depending on where you stand. For a two-dimensional creature living on a balloon, that balloon is a manifold. For us, three-dimensional beings, the universe itself might be one, vast and invisible, yet with contours that can bend and stretch. To picture it, imagine being inside a room so large that you cannot see its walls. No matter how far you walk, the floor beneath you feels flat. But if you could travel far enough, you might eventually return to where you started without ever crossing a visible edge. That's the essence of a curved space, endless, yet finite, like the surface of a sphere but in dimensions beyond your senses. Riemann's mathematics gave form to this invisible shape. His equations, though simple to him, were filled with meaning. They described how distances change when space itself is not uniform. But we don't need the symbols to understand what he meant. We can think of it this way. In a curved world, light no longer travels in perfect straightness. It bends gently, following the paths carved by the shape of the space around it. That one thought, that even light can curve without a force tugging at it, would one day explain the orbits of planets, the bending of starlight near massive bodies, and even the expansion of the universe itself. But Riemann didn't live to see his ideas fully recognized. His health was fragile, and he died young, before his 41st birthday. He left behind a handful of papers, a few lectures, and a legacy that would echo through physics for the next 2 centuries. What remains most haunting about Riemann's story is how quietly it unfolded. There were no grand observatories, no metal mirrors, no applause, just thought, deep, patient thought, turning into revelation. He once described geometry not as a set of laws, but as a freedom of imagination, where the mind could wander through invisible landscapes and give them form. To him, mathematics was not about solving, but about seeing, about glimpsing structures that might exist beyond our senses. If you imagine sitting beside him during those long nights of work, you might see a candle flickering over his notes, the faint smell of ink and parchment, and the soft rustle of paper as he sketches lines that curve into dimensions no human has ever seen. Outside, the stars move silently across the sky, unaware that someone below is beginning to understand the shape of the very space they move through. When Einstein later built his theory of relativity, he used Riemann's geometry as his foundation. The same equations that once described abstract shapes now described gravity, motion, and the expansion of the cosmos. Riemann's imagination had quietly given the universe its blueprint, and so, in a way, Riemann became the first cartographer of the invisible, the one who drew the map for space itself. As we drift further into the story, the path now carries us toward the man who took Riemann's dream and made it real. The mathematician's abstract curves will soon become Einstein's living universe, a place where time and space entwine, and where gravity is nothing more than the gentle bending of everything that exists. By the time Albert Einstein began to wonder about gravity, the universe already had a map, but not yet a heartbeat. The geometry of Riemann had given space its potential to bend, to ripple, to hold shape. Yet no one had connected those elegant mathematical curves to the everyday pull that kept feet on the floor and planets in their orbits. Gravity, for all its familiarity, was still an invisible mystery. Einstein was not a man of laboratories or machines. His tools were patience and thought. He often said that he learned best not by doing experiments, but by daydreaming. And so, one day, he imagined a simple scene: a man falling from a roof. What does that man feel as he falls? For a few moments, Einstein realized he feels nothing at all. The weight of his body disappears. The floor drops away, and gravity, which moments earlier held him down, seems to vanish. It was a strange contradiction. Gravity disappears precisely when you're moving most completely under its influence. From that small thought grew one of the most powerful insights in science, what Einstein called the principle of equivalence. He proposed that gravity and acceleration are in a sense the same thing. If you are sealed inside a windowless elevator, you cannot tell whether the pull you feel is from gravity or from the elevator rising through space. The two experiences are indistinguishable. This was a clue, a whisper that gravity might not be a force at all, but a feature of space itself. Einstein began to think of space and time not as separate, but as a single, unified fabric, space-time. And like any fabric, it could stretch, fold, or bend. If a massive object like a star or a planet pressed upon that fabric, it would create a kind of well, a dip. Other objects nearby would follow the curves of that dip, not because they were being pulled, but because the geometry of space itself guided their motion. He once explained it with a smile, saying that matter tells space how to curve, and space tells matter how to move. You can picture it with a simple image. Imagine a large rubber sheet stretched tight. Place a heavy ball in the middle. That's a star. The sheet dips under its weight. Now roll a smaller marble nearby. It will circle the dip not because the larger ball exerts a mysterious tug, but because it follows the slope in the surface. That's gravity, not as an invisible rope pulling objects together, but as the graceful dance of geometry itself. When Einstein first presented this idea in 1915, the world didn't quite know what to do with it. His general theory of relativity was beautiful but bewildering, a set of mathematical relationships describing how mass, motion, and the very shape of space are woven together. The equations looked like a foreign language, yet they sang with symmetry and elegance. But beauty alone isn't enough for science. A theory must make predictions that can be tested, and Einstein's theory did. It predicted, among other things, that light itself, which has no mass, should bend when it passes near a massive body like the sun. Not because light is pulled, but because the space it travels through is curved. For years, this remained an untested dream, until a solar eclipse in 1919 offered the perfect chance. During the eclipse, the sun's light would be blocked, allowing astronomers to photograph distant stars near its edge. If Einstein was right, those stars would appear slightly displaced from their normal positions. The effect of light bending along curved space-time. The expedition was led by the English astronomer Arthur Eddington. He travelled to the island of Principe, off the coast of Africa, hauling fragile cameras and glass plates across oceans for a few minutes of darkness. When the eclipse came, clouds threatened to ruin everything. But at the last moment they parted just long enough for Eddington to capture the photographs. Months later, the results were announced. The stars had indeed shifted just as Einstein's theory predicted. The amount of bending matched his calculations exactly. Overnight, Einstein became a global symbol of genius. Newspaper headlines declared, "Revolution in science, Newtonian ideas overthrown." Crowds gathered outside his lectures. Children learned to recognize his hair before his name. But behind the sudden fame, the truth remained quiet and profound. Einstein had done more than replace one law with another. He had transformed the very meaning of gravity. What once seemed like an external force was now seen as the natural flow of space itself. The cosmos was no longer a collection of objects moving through emptiness. It was a living fabric shaped and reshaped by everything within it. If you could somehow step outside that fabric and watch the universe from above, you would see stars and planets curving the geometry of space-time, and light weaving through those curves like silk through wind. Every orbit, every fall, every ripple of gravity is part of that cosmic choreography. Even the passage of time is not immune. Near a massive body, a planet, a black hole, time itself slows down. Not because clocks run differently, but because time is part of the fabric, stretched and compressed by curvature. A second near a star is not quite the same as a second in deep space. Time, like light and motion, bends. Einstein's discovery reshaped not just physics, but philosophy. The universe was no longer a static stage, but a performer, dynamic, interactive, alive. Space could stretch. Time could flow differently. Nothingness could have shape. He once said that he felt a deep sense of harmony when thinking about how the cosmos worked. That harmony came not from perfection, but from connection. The way every part of reality influences every other part. Today, every GPS signal, every satellite orbit, every image from a distant galaxy relies on Einstein's insight. His geometry of gravity keeps our technology synchronized and our understanding aligned with the real rhythm of space. But perhaps the most beautiful legacy of his work is how it restores wonder to emptiness. Space is not a void, not a stage waiting for actors. It is an ocean with waves, a fabric that hums quietly with motion, shaped by every star and every heartbeat. If you stand under the night sky and imagine the planets circling, the stars drifting, and the galaxies expanding, you can almost feel it. The slow, silent pulse of curved space-time beneath everything. And as we drift further into the story, that pulse will guide us toward its next revelation. That this fabric, this gentle curvature of reality is not static. It stretches, it expands, and somewhere in its vast unfolding lies the beginning of everything, the origin of the universe itself. The night sky, so still to the naked eye, was hiding a secret motion. For centuries people had imagined the stars as steady lanterns, ancient unmoving lights against a silent backdrop. Even when telescopes revealed galaxies by the thousands, the universe still seemed eternal, balanced, and complete. But in the quiet years after Einstein's great discovery of curved space, a few curious minds began to suspect that stillness might be an illusion. Among them was a tall, soft-spoken man with a keen sense of precision and a hint of restlessness. Edwin Hubble, working again at his mountain observatory above Los Angeles. His massive telescope at Mount Wilson, the same that had revealed Andromeda's true nature, was now turned toward other faint smudges in the sky. Those smudges, he knew, were galaxies, vast collections of stars far beyond the Milky Way. And what he wanted to know was whether they were moving, and if so, how? The answer would come not from motion we could see with our eyes, but from motion hidden in light itself. When a sound source moves, its pitch shifts. An ambulance passing by changes from a high wail to a low hum as it moves away. Light behaves in a similar way. When a star or galaxy moves toward us, its light is shifted slightly toward the blue end of the spectrum, and when it moves away, the light stretches toward red. Astronomers call this effect the redshift, not because the galaxies turn red, but because the wavelengths of their light lengthen, like threads of colour being gently pulled apart. It's a small change, invisible to the human eye, but detectable with instruments that split light into its rainbow of components. By studying those subtle rainbows, Hubble began to notice something extraordinary. Nearly every galaxy he observed showed a redshift. Each one was moving away, not randomly, but in every direction. And the farther a galaxy was, the greater its redshift. Its light was stretched more, as though space itself had taken a deep breath and sighed. At first, it didn't make sense. How could everything be moving away from everything else? If space were like a room, some galaxies might move north, others south, but not all in all directions at once. The only way for that to be true, Hubble realised, was if the room itself were growing, if the fabric of space was expanding, carrying the galaxies with it like raisins floating in rising dough. It was a quiet but revolutionary thought. The universe was not static. It was alive, dynamic, changing with time. The implications rippled outward. If space was expanding now, then in the past it must have been smaller. If you could rewind the cosmic film far enough, all galaxies, all stars, all matter would have once been gathered in a single, unimaginable state. Not a place within space, but a moment before space itself existed. Hubble's data offered the first tangible evidence that the universe had a beginning, that it had, at some point, expanded from something compact and brilliant into the vastness we see today. When Einstein heard of Hubble's discovery, he was both amazed and regretful. Years earlier, his own equations of general relativity had hinted that the universe could not be static, that space should either expand or contract. But Einstein, believing the cosmos to be eternal and unchanging, had adjusted his equations to force balance. He added a term called the cosmological constant, a mathematical fix designed to hold the universe steady. Now, faced with Hubble's redshifts, Einstein visited Mount Wilson himself. Standing beneath the Great Telescope, he's said to have turned to Hubble and admitted, "My biggest blunder." He had tried to keep the universe still when it was never still at all. It's strange to think that even Einstein, the man who had shown the universe could bend, still couldn't imagine it could breathe. Today we know that Hubble's discovery marked a profound turning point. The light he studied, stretched and thinned by the growing fabric of space, became the first clue that the cosmos is not timeless. It has a history. It evolves. The stars we see tonight are part of an ongoing story that began long before us and continues to unfold with every passing second. If you could look at the universe as a whole, if you could somehow step outside of it and watch, you wouldn't see galaxies rushing through space like ships through water. Instead, you'd see space itself expanding, the distances between galaxies growing as the cosmic fabric stretches. It's not that the galaxies are moving away from us, it's that the very distance between everything is increasing. Imagine dots on the surface of a balloon. As you blow air into it, the balloon expands and the dots move apart. None of them are flying through the surface. It's the surface itself that's growing. That's the universe. No center, no edge, just space expanding everywhere at once. And yet, even in its expansion, the universe preserves a kind of stillness. From any point in space, it looks the same in every direction. Every galaxy sees the others receding. Every observer feels at the center of the unfolding. It's a cosmic illusion born of symmetry, and somehow it's comforting. A reminder that we are all equally woven into the same expansion. In the years that followed, Hubble continued to refine his measurements, tracing the relationship between a galaxy's distance and its redshift. The pattern was beautifully simple. The farther away a galaxy is, the faster it appears to recede. That relationship became known as Hubble's law, though in truth it's less a law and more a melody, a rhythm played across the universe, the tempo of cosmic growth. The numbers are staggering, but we can think of them softly. For every 3 million light-years of distance, the space between us grows by about 70 kilometers per second. It's like the universe inhaling, gently but without end. If you step outside tonight and look at the stars, you're gazing into that slow expansion. The light you see has been stretched across billions of years. Each colour, each glimmer carries a history of travel through space that has itself been changing as it journeyed. That red glow from a distant galaxy is not just light from a faraway world. It's the echo of expansion, the memory of motion written in colour. Hubble once said that his greatest joy was not in proving a theory, but in revealing something so simple that it must have been there all along. His expanding sky was exactly that. Not a trick of mathematics, but the unveiling of what had always been true, that the universe moves not through space, but with it. And so, as we drift further into the story, we follow that expansion back in time, to when all light and matter were one, when the sky itself glowed like a sunrise without end. The path now carries us toward the moment of illumination, the first dawn, the birth of everything, when the universe itself caught fire and began to shine. If Hubble's discovery showed us that the universe is expanding, then the next question was as simple as it was profound. Expanding from what? To imagine that answer, you have to think of time itself running backward, like watching a wave retreat along the sand. Every second you rewind, the galaxies move closer, the distances shrink, the spaces between stars collapse, the night becomes brighter as everything condenses. Keep rewinding further, and the scattered stars merge into glowing clusters, the clusters into searing clouds, until at last all matter, energy and light blur together into a single, brilliant storm. There is no sound in that scene, no space to echo it, no time as we understand it. It's not an explosion in the sky, it is the sky. It's not that something burst into the universe, it's that the universe itself burst into being. We call this moment the Big Bang, though the name is misleading. There was no bang, no outward explosion. It was the quiet birth of distance itself, space stretching from a point smaller than any atom, hot beyond measure, glowing with the first light. If you could have seen it, though of course there was no seeing then, the entire cosmos would have been a blinding sea of light and plasma, particles of matter and light intertwined, constantly colliding, separating and colliding again. The early universe was not dark. It was an ocean of brilliance, and yet it was still expanding. As it stretched, it cooled. Like the breath leaving a furnace, the cosmic heat began to soften. After roughly 400,000 years, an infant heartbeat compared to the age of the cosmos, something extraordinary happened. For the first time, light was free. Before that moment, the universe was opaque. Photons, the particles of light, could not travel far before crashing into particles of matter. But as the universe cooled, those particles began to join into the first simple atoms. With that, the fog lifted. The light could finally move, streaming outward across the growing universe. That first light is still travelling. It never stopped. Over billions of years, as space continued to expand, that light stretched with it. Its once blazing glare softened, its wavelengths lengthened, until what began as white fire became a faint invisible glow in the microwave range. It is everywhere, all around us. You can't see it, but it bathes the entire universe like the dim warmth that lingers after sunset. Astronomers call it the cosmic microwave background, or CMB, the oldest light in existence, the afterglow of creation itself. If you've ever turned an old television to a channel with no signal, the faint static and hiss that fills the screen is mostly electronic noise, but about 1% of it is something else. It's the whisper of that first light, arriving after nearly 14 billion years. Every flicker of that static carries the memory of the moment the universe became transparent. In the 1960s, two engineers, Arno Penzias and Robert Wilson, accidentally discovered it. They were testing a radio antenna in New Jersey when they heard a persistent background noise, a hiss that came from every direction, day and night, unaffected by weather or location. At first, they thought it might be a problem with the equipment. They even cleaned out a family of pigeons nesting inside the antenna, thinking the birds might be the cause. But the sound remained. Eventually they realized what they had found. It wasn't noise, it was a message, the stretched out echo of the first light. They had stumbled onto the living memory of the universe itself. Today, we can map that ancient glow in exquisite detail. Satellites like COBE, Dobosmap and Planck have revealed a sky painted with subtle ripples. Tiny variations in temperature, 1 part in 100,000. Those ripples are the fingerprints of the early cosmos, showing where matter first began to gather, the seeds from which galaxies and stars would grow. When we look at those maps, we're not just seeing light, we're seeing time, a snapshot of the universe when it was only a few 100,000 years old. It's the closest we can ever come to a photograph of the beginning. Think of it this way. When you look at the sun, you see it as it was 8 minutes ago, the time it takes light to travel from its surface to your eyes. When you look at the nearest star, you're seeing it as it was years ago. But when you look at the cosmic background, you're seeing light that has been travelling for almost 14 billion years. That glow is older than Earth, older than the stars, older than the very idea of darkness. And what it tells us is simple but astonishing. The universe had a beginning, a moment when it became bright. From that moment on, everything we know, every atom, every star, every planet, every living thing, unfolded. The hydrogen and helium formed first, the raw material for future suns. Gravity began its slow work, pulling those gases into clumps, igniting the first stars. The stars forged heavier elements in their hearts, carbon, oxygen, iron, and when they died, they scattered those elements into space. In time, those ashes would form new stars, new worlds, and eventually us. All of it, every thought, every sound, every heartbeat, is a continuation of that first light. There's something quietly humbling about it. Every photon that shines on your skin, every ray that warms the earth, can trace its lineage back to that moment of freedom, when the universe first became transparent and let light move. The night sky, then, is not truly dark. It glows faintly with that ancient fire, stretched and softened beyond our senses. Every time you look up, you're seeing not just stars, but the remnant warmth of creation itself. And so, when you turn on an old television and see that gentle static, you are, in a very real sense, watching the birth of the universe. The hiss between channels is the echo of a beginning so vast, so bright, that it still lingers everywhere, even in the quiet air of your living room. As we drift further into the story, our path carries us toward that darkness, not as emptiness but as evidence. We'll explore why the night sky is dark at all and why that darkness, far from being absence, is proof that the universe has not existed forever. It's the quiet that follows the first song, the shadow that gives the light its meaning. For all its ancient brightness, the universe we see tonight is wrapped in darkness. Between the stars lies a deep, endless black, broken only by faint pinpoints of light. To early thinkers, this darkness was a mystery that seemed to contradict reason. If the cosmos were infinite and filled with stars, they asked, why isn't the night sky blazing with light? Shouldn't every direction end in a star? That question, the riddle of the dark night, haunted astronomy for centuries. It's called Olber's paradox, though the name belongs less to one man than to an idea that quietly waited for the right moment to be understood. The answer, it turns out, was hidden not in the stars but in time itself. The reason the night sky is dark is simple and astonishing. It's because the universe had a beginning. When you look at the stars, you're not seeing them as they are but as they were. The light from the sun, for instance, takes 8 minutes to reach us. The light from the nearest star takes more than 4 years. From distant galaxies, the light may have been travelling for billions of years. That means when we look deeper into space, we're also looking deeper into the past. Now imagine travelling backward with that light. The farther you look, the younger the universe becomes, until you reach the moment of first light, when everything was hot and glowing. Beyond that, there is nothing to see because there was no before in any familiar sense. The darkness beyond that boundary isn't a veil hiding more stars, it's the limit of time itself. The night sky is dark because the universe hasn't existed forever. The stars haven't had enough time to fill it with light. It's a humbling thought that the darkness above you isn't empty. It's simply light that hasn't arrived yet. We live, in a sense, inside a great cosmic sunrise that is still unfolding. The glow of the first fire is still spreading across space, still softening into the faint warmth we call the cosmic background. The stars and galaxies that shine tonight are like small lanterns rising from that fading dawn. If the universe were eternal and unchanging, every line of sight would end on the surface of a star, and the sky would blaze with endless brightness. But because it began in a finite moment, because it has an age and an expanding boundary, there are vast regions whose light has not yet reached us, and may never do so. Astronomers call this region around us the observable universe, the portion of space from which light has had time to travel since the beginning. It's not the whole cosmos, just the part that can touch us with light. Imagine standing in the centre of a slowly growing bubble, where the edge marks the farthest distance light could have crossed in nearly 14 billion years. That shimmering boundary is not a wall, it's simply the horizon of what we can know. Everything inside that horizon, every galaxy, every cluster, every delicate strand of cosmic web, is part of our visible dawn. Everything beyond it is hidden in silence, waiting, perhaps forever, beyond the reach of our instruments and imagination. And even within this vast bubble of light, much remains dark. Between the galaxies lies matter we cannot see. Dark matter, invisible yet detectable through its pull on stars. And beyond that, an even more mysterious presence. Dark energy, driving the universe to expand faster and faster. The irony of the cosmos is that the more we illuminate, the more hidden it becomes. But the darkness, far from being a void, is meaningful. It's a reminder that we live in a young universe, still growing, still unfolding its story. The starlight that reaches us tonight is only a small fraction of all that exists. A few notes from a much larger symphony, still playing beyond our hearing. Sometimes, when you look at the night sky, it feels timeless, eternal, unmoving. But every photon that touches your eyes has travelled across billions of years. The faint glimmer you see from a distant galaxy tonight began its journey before Earth even existed. Some of that light has crossed so much expanding space that its colour has stretched into invisible red, joining the cosmic background itself. The universe is not just glowing, it is cooling, its light fading gently as it grows. That slow dimming is why the night feels serene. The stars you see are the survivors of a great fire that once filled everything. The darkness between them isn't absence, it's peace. If you could see with eyes that captured all wavelengths of light, the night would not be black at all. It would shimmer softly with microwaves, hum faintly with radio waves, and glow faintly with the leftover warmth of the first dawn. Even now, in the emptiest patch of sky, the universe still glows, a whisper of the light that once was. It's strange, isn't it? We often think of night as the time when light disappears, but in truth, it's the moment we are surrounded by ancient light too stretched, too faint for our eyes to see. That faintness carries its own kind of beauty. It means the cosmos is not infinite in age. It's young enough to remember its beginning. The darkness is the echo of that youth, the stillness that follows the first song. If you close your eyes for a moment and picture the entire universe as a single day, from its fiery birth to its quiet expansion now, humanity appears just seconds before midnight, a flicker of consciousness in a long and luminous night. And yet, even in that brief instant, we have managed to understand the meaning of the dark above us. So when you step outside and feel small beneath the stars, remember that smallness is not insignificance, it's connection. You're looking at the edge of time, the farthest reach of light, the border between the known and the unknown. You're inside the dawn, surrounded by light still travelling home. As we drift further into the story, our gaze widens once more. From the quiet beauty of this finite night, we'll move to the vast pattern that has emerged within it, the delicate structure that gravity and time have drawn across the cosmos. The path now carries us toward the grand design of the universe, the luminous filaments of galaxies that thread together like frost forming on a window pane, the cosmic web and the breath of time that still shapes it. If the night sky could be peeled back like a veil, you would see something astonishing. Not empty space, but a vast and intricate structure, a pattern stretching farther than imagination. Astronomers call it the cosmic web, a delicate network of galaxies and clusters linked together by invisible threads of gravity. From a distance, it looks almost like lace, luminous knots connected by faint filaments surrounding enormous hollow voids. The galaxies are not scattered randomly. They gather in these strands, following the ancient pull of matter that has been weaving the universe since its earliest moments. To understand how this web formed, we must go back to the faint ripples in the cosmic background, the tiny temperature differences we spoke of earlier. Those gentle variations, only one part in 100,000, were the seeds of everything. Where the light was slightly denser, gravity began to pull harder, drawing in matter, deepening the dimples in the fabric of space. Over billions of years, those dimples became rivers of galaxies, flowing together into great clusters. The invisible scaffolding of dark matter, unseen but immense, guided the motion. If normal matter is the paint on the canvas, dark matter is the canvas itself, shaping where the paint can go. We can't see dark matter directly. It doesn't shine or reflect light, but its gravity leaves fingerprints, subtle warps in the paths of light travelling from distant galaxies, distortions that astronomers can map like ripples on a pond. From those distortions, we've learned that dark matter forms the skeleton of the cosmos, while the visible stars and gas trace its outline. Imagine, for a moment, standing far outside the universe, able to see it all at once. You wouldn't see planets or stars, not even galaxies, but a glowing fog of light and structure, threads and clusters stretching in every direction. It would look like frost forming on glass, or the tangled filaments of a spider's web glistening with dew. This is the large-scale architecture of the cosmos, drawn by gravity, painted by time. Even now, new galaxies continue to drift and merge along these filaments, forming clusters where the intersections thicken. At those crossroads, gravity is strongest, and the galaxies spin around each other like dancers circling an invisible centre. Between them lie immense voids, regions so empty they could contain hundreds of galaxies and yet remain dark and silent. If you think of the universe as a living thing, this web is its nervous system, vast, delicate and full of slow, graceful motion. It is the frozen memory of creation, stretched thin by expansion but still holding the shape of its earliest vibrations. Scientists have recreated this process in computer simulations, condensing billions of years into minutes of visual time. They start with a nearly uniform mist, the early universe just after its birth. Then they let gravity do its patient work. Slowly, the mist begins to clump. Filaments form. Clusters bloom. The universe takes on structure, as if sculpted by invisible hands. Watching those simulations is like seeing time breathe, a cosmic inhale and exhale, forming galaxies with every breath. Each filament in this web is composed of thousands of galaxies, each galaxy containing hundreds of billions of stars. And within those stars orbit planets, and upon at least one of them, ours. The web has grown eyes to look back at itself. There's a quiet poetry in that. The same forces that shaped the clusters and voids also shaped you. The iron in your blood, the calcium in your bones, the oxygen you breathe. All were forged in stars that gathered along these filaments, born in the bright knots of this cosmic tapestry. We are not outside the pattern, we are part of it, small but connected to everything. Over time, the web has continued to stretch. The galaxies drift farther apart as the expansion of space accelerates. Gravity still binds local clusters together, but across vast distances the tug of attraction grows weaker. The universe is slowly becoming more spacious, more diffuse, more quiet. The cosmic web, though immense, is not eternal. In the far future, its strands will thin, the bright intersections fading as galaxies burn out and drift away beyond the horizon of sight. The grand structure will remain, but dimmed, its once vivid filaments dissolving into the darkness from which they first arose. And yet, even that fading has beauty. It is the universe exhaling, releasing the light it once held. Every life has its rhythm. Stars are born, they shine, they fade, and from their ashes new worlds form. The cosmos itself seems to follow that same rhythm, breathing across billions of years. If you could somehow listen to the universe, not with ears but with awareness, you might hear that breath. The low hum of expansion, the faint crackle of ancient light, the slow drift of galaxies across invisible strands. It is a sound beyond sound, a music of time written into the geometry of everything. When astronomers map the cosmic web, they're not just charting positions, they're tracing the story of gravity's patience. Each thread is a record of what happens when chaos is given enough time to find balance. What began as randomness has settled into harmony. It's a reminder that structure doesn't always need design, that beauty can emerge from quiet persistence. And perhaps that's the lesson this cosmic lace offers us, that even in vastness there is order, even in silence, connection. The galaxies may be drifting apart, but they still form part of a single pattern, written in the language of time. The same is true of us. Our lives, brief and flickering as they are, leave traces in the larger fabric, threads of memory, influence, love. The universe doesn't waste anything. It reuses every atom, every photon, every moment. We're all strands in the same web, made of the same light. As we drift further into the story, our path now carries us toward the edges of that web, toward the quiet, accelerating expansion that will one day stretch these threads almost beyond recognition. The next chapter of the cosmos is not one of brightness, but of gentle fading, a slow widening of distance, a lengthening of silence. There, in that deep future, the universe will become something softer, quieter, a place where even light must struggle to cross the growing distances between what remains. But for now, the web still glows, fragile and alive. The frozen breath of time still visible in the dark. The universe, once bright and dense and roaring with energy, is now slowing into quiet. Galaxies drift apart like lanterns carried down a widening river. The light between them stretches thinner with every passing billion years. To us it still feels eternal, the sky full of stars, the constellations unchanging, but on cosmic timescales, the night is gently exhaling. In 1998, astronomers studying distant supernovae, colossal stellar explosions that briefly outshine entire galaxies, made an unexpected discovery. They had been measuring how fast the universe was expanding, expecting that gravity, the ever-present pull of matter, would be slowing it down. But what they found was the opposite. The expansion was speeding up. It was as if the universe had taken a deep breath and instead of relaxing had started to stretch faster. To explain this, scientists propose the existence of something unseen, a mysterious pressure that pushes galaxies apart rather than pulling them together. They called it dark energy, though the name captures more mystery than meaning. We don't know what it is. We only know that it fills space itself, silent but relentless. If gravity is the universe's slow embrace, dark energy is its gentle release. Together they shape the balance of everything, one pulling matter into clusters and stars, the other urging it to drift away into the dark. It's tempting to imagine dark energy as a wind, but it isn't a wind at all. It doesn't blow, it simply is. It's the quiet expansion of the fabric of space itself, growing more spacious with every heartbeat of time. When the discovery was announced, many physicists were stunned. Einstein, decades earlier, had added a small correction to his equations, a mathematical trick called the cosmological constant, to keep the universe static. He later called it his biggest blunder. But now it seemed he might have been right after all. That constant, representing the energy of empty space, could explain the accelerating expansion. The very nothingness of the universe might contain within it the power to drive galaxies apart. And so, the cosmos, born in fire and light, continues to stretch into quiet. If you could speed up the clock of the universe, compressing billions of years into seconds, you'd see the galaxies retreat from each other like sparks from a dying ember. One by one, their lights would fade beyond visibility, swallowed by distance and time. In a few trillion years, long after the sun, the earth, and even memory itself are gone, our corner of the universe will grow lonely. The great clusters that now adorn the sky will vanish beyond the cosmic horizon, too far for their light to ever reach us. Only our local group, the Milky Way and its small companion, will remain, slowly merging into a single quiet galaxy, adrift in a sea of black. It won't happen with drama or destruction. It will happen softly. The sky will dim, the stars will age, and the distances will grow. The universe will not collapse. It will fade. Astronomers sometimes call this far future the era of darkness, but the phrase doesn't quite capture its beauty. The cosmos won't end with a crash. It will end with a sigh. In that distant age when the galaxies have slipped beyond sight, there will be no new light to fill the night. The cosmic background will cool into silence, its faint microwave whisper stretched into radio waves, then into wavelengths too long for any instrument to detect. The echo of creation will still exist, but too quiet for any ear, natural or mechanical, to hear. The stars we see tonight are the lucky ones, their light still able to find us across the gulf. Most of the light that ever shone will never reach another eye. In a way, that makes each visible star a small miracle, a messenger that made it through before the growing quiet closed in. It's easy to think of this as sad, but perhaps it's just another form of peace. The universe, after all, has been busy for nearly 14 billion years, expanding, cooling, building galaxies, igniting stars and making life. Everything that rises must eventually rest. Maybe the expansion's acceleration is not an ending, but a kind of cosmic exhalation, the moment when creation finally allows itself to slow into calm. Dark energy, then, is not a villain. It is the lullaby that follows the fire. When you look at the night sky and feel that peculiar stillness, that sense that everything is vast yet somehow gentle, you're feeling the universe as it is, not static, but serenely unfolding. Space doesn't rush. It stretches so gradually that even light, the fastest thing we know, barely keeps pace. And still, there is something intimate in that silence. Even as the galaxies drift apart, the atoms within them, within us, remain bound. Inside each person, the ancient forces of gravity, electromagnetism and nuclear fire still hold their delicate balance. The same physics that shapes the cosmos also shapes your heartbeat. The expansion of the universe may stretch galaxies, but it does not stretch the quiet bond between matter and memory. Perhaps that's what makes the knowledge of dark energy so strangely comforting. It reminds us that even as everything drifts apart, the act of noticing, of wondering, connects us. Our awareness is a thread of gravity all its own, holding us to the stars we can no longer reach. When astronomers describe the far future, they sometimes say the universe will go dark. But that phrase misses something crucial. Darkness isn't the absence of light. It's the canvas on which light can still be remembered. The photons that reach your eyes tonight, from stars billions of years gone, are proof that even in a universe that expands into silence, light finds a way to linger. If you step outside and look up, every star you see is already part of the past. Their light began its journey long before you were born. And yet, in this very moment, it meets you. A union of two times, two places, separated by unimaginable distance, yet connected through the persistence of light. So perhaps the expanding silence isn't something to fear. It's an invitation, a reminder that every moment of awareness is precious, every glimpse of starlight a gift from a universe that is slowly learning to rest. As we drift further into the story, our path turns inward again, away from the galaxies and toward the spaces between them. What we call nothing may not be empty at all. Beneath that quiet, scientists have found a deeper rhythm, a faint hum inside the void itself. The next chapter of our journey takes us there, into the whispering vacuum where even silence is alive. We've drifted so far into the quiet that now we find ourselves face to face with what seems like nothing at all. But as it turns out, nothing is one of the most complicated ideas in science. When you look into the darkness between the stars, it's tempting to imagine true emptiness, a vast silent void where no particle moves and no light crosses. Yet, according to the strange laws that govern the very small, that darkness isn't truly empty. It hums. Even the most perfect vacuum, a space stripped of all matter, colder than any winter ever felt, is alive with invisible motion. Tiny fluctuations shimmer in and out of existence, too brief to see, too subtle to touch. These are the virtual particles, ghostly ripples that appear, vanish, and appear again, like thoughts passing through a dream. Quantum physics tells us that the universe doesn't allow absolute stillness. At every point in space, there's a kind of restless uncertainty, a background murmur of creation and destruction happening endlessly. If you could somehow listen to the vacuum, it would whisper. The physicists who first discovered this were both astonished and uneasy. It meant that what we call empty space is actually full, filled with energy and fleeting possibility. The vacuum is not a blank stage, it's a restless sea, constantly foaming with spontaneous activity. You can picture it like the surface of the ocean on a windless night. To the eye, it seems smooth, still. But if you could see closer, much, much closer, you'd find that even calm water trembles with tiny ripples, molecules jostling, waves forming and collapsing faster than any heartbeat. That's the quantum vacuum, a sea so alive that its smallest ripples give birth to the structure of everything. In fact, these quantum fluctuations are believed to have shaped the universe itself. When the cosmos was young, unimaginably small, still glowing with the fire of its own birth, these microscopic ripples were stretched to cosmic size by a brief and powerful growth spurt known as inflation. Imagine blowing a balloon so rapidly that even the smallest specks of dust on its surface become continents. In the same way, the quantum fluctuations in that newborn universe were magnified, frozen into the fabric of space. Those faint variations became the seeds from which galaxies would one day form, tiny imperfections that grew, over billions of years, into the grand cosmic web we see now. The stars, the clusters, even the shape of the night sky, all trace their ancestry back to those quiet quantum whispers. It's a staggering idea that the structure of the entire universe, all its beauty, all its order, may have begun as a flicker of uncertainty, a vibration inside what we call nothing. But even that word, nothing, starts to feel slippery here. If a vacuum is full of restless energy, can we still call it empty? If it can give rise to particles, light, and even entire universes, then perhaps nothing is not the absence of being, but the potential for it. Physicists sometimes describe this energy as the zero-point field, the lowest possible level of activity in the quantum world. It's the hum that remains even when everything else is taken away. To make sense of it without equations, you can imagine the universe as an infinite orchestra. Each particle is a note, each field a vibration. Even if every instrument stopped playing, there would still be the faint resonance of silence itself, a sound that isn't nothing, but the memory of everything. This quiet energy may even connect to the dark energy we met earlier, the mysterious force driving the universe's expansion. Perhaps the vacuum's quantum hum is what pushes galaxies apart, its invisible rhythm rippling through space-time. If that's true, then every breath of empty air around you carries a trace of the same energy that is widening the cosmos, and yet, for all its profundity, the vacuum remains elusive. We can't see it, only its effects. It's like wind in a field, invisible, but revealed by the sway of grass. In laboratories, scientists have detected small hints of its presence through experiments that measure the subtle forces between metal plates in a vacuum. Even when space is supposedly empty, something, some gentle push, remains. That push, that flicker, that hum, all of it suggests that reality may be built not on solid foundations, but on a kind of shimmering uncertainty. Nothing is truly still. Even stillness itself is movement, waiting to become something more. If you let that thought settle, it becomes strangely comforting. The universe is not built on void, but on possibility. The same creative pulse that gave rise to galaxies also fills every inch of space around you. What seems silent is full of quiet life. You can think of it like this. Between every heartbeat of existence there is a pause, a space where nothing seems to happen. But in that pause lies everything that will happen, the potential for stars, for light, for thought. The quantum vacuum is that pause on a cosmic scale, the stillness that contains the seed of every future moment. It reminds us that beginnings do not always come with noise or light. Sometimes they arrive in whispers. When we trace the universe backward to its first instant, we find ourselves standing on the edge of that whisper, a moment when fluctuations in the void became the spark of time itself. Out of what seemed like nothing, the cosmos breathed its first breath. And if that's true, then nothing is not something to fear. It's not the end, but the beginning. The vacuum is a kind of quiet womb, endlessly creative, endlessly patient, always humming beneath the surface of reality. Everywhere you go, even in the spaces between atoms, that hum continues. Every point in the universe, no matter how empty it seems, holds the same deep potential. As we drift further into the story, the path now carries us gently from the physics of emptiness back to the poetry of presence. Our next step isn't about stars or galaxies, but about us, the beings who can sit under this vast sky and imagine all of it. From the first spark in the vacuum to the light in your mind, the universe's wonder has come full circle. Our next chapter will explore that circle, the quiet connection between the infinite and the intimate, between the cosmos and the consciousness that can dream of it. Across the long arc of time, the universe has gone from fire to frost, from a radiant blaze of light to the cool, expanding silence we see now. And yet, here on this small planet, orbiting an ordinary star, the cosmos has done something remarkable. It has begun to think about itself. That is what you're doing at this very moment, participating in the oldest, most improbable experiment in existence, awareness. The atoms that once drifted through nebulae, that burned inside stars, that scattered in supernovae, have gathered here in you to ask the question why. It's strange when you think about it. For billions of years, the universe unfolded without words, without thought, without a single conscious witness. Then, in a small corner of space, it began to notice its own patterns. Creatures evolved eyes to capture light, ears to sense vibration, and minds to weave meaning from both. When Thomas Digges erased the walls of the firmament and set the stars adrift in infinity, he was doing what humans do best, turning wonder into understanding. When Herschel and Caroline polished mirrors until they could drink the faint light of distant suns, they were translating curiosity into craft. When Henrietta Leavitt counted the pulses of stars and found rhythm in their brightness, she was hearing the heartbeat of the cosmos. And when Einstein bent space and Hubble measured its expansion, they were simply continuing that same long conversation, the universe talking to itself through the minds it made. It's easy to forget in the flood of equations and discoveries that science is not about certainty, it's about awe. Every answer we find leads to deeper questions. Each glimpse of the infinite widens the horizon just enough for mystery to remain. Maybe that's why the night sky feels both humbling and comforting. You're looking at something unimaginably vast, but you're also looking at something you belong to. The same laws that govern galaxies govern your heartbeat. The same particles that drift in the void form the breath in your lungs. You're made of the same light that left ancient stars and travelled across the ages to touch your eyes. It's often said that humans are made of stardust. That phrase is true, but incomplete. You're made not just of the stars' material, but of their story, of their birth, their fusion, their death, and the quiet dispersal of their ashes into space. You're part of a continuity that stretches back to the first spark of creation. When you look up at the stars and feel that sudden stillness, that sense of both smallness and belonging, you're experiencing what philosophers once called the sublime, the moment when comprehension and emotion blend into something beyond both. The stars are not there to make you feel insignificant. They are there to remind you that even insignificance can be luminous. It's remarkable that our small minds can even grasp a fraction of it, that folds of neural tissue inside our heads can imagine the curvature of spacetime, or the birth of galaxies billions of light years away. We are tiny, yes, but our imagination is vast. In that way, we mirror the universe itself, finite in size, infinite in depth. Sometimes, when astronomers speak of scale, distances measured in trillions upon trillions of kilometers, it's easy to feel detached, as if we're observing something cold and far away. But perhaps that's the wrong perspective. Perhaps the correct view is not from outside, but from within. Because everything you see, everything you measure, everything you know, it's all part of the same fabric. When you gaze at a star, the light that enters your eye becomes part of you. In that instant, you and the universe are not separate. You are two halves of one observation, each completing the other. It's a thought that blurs the line between science and poetry. The universe observes itself through consciousness. Matter becomes aware, and awareness in turn gives meaning back to matter. If there is anything eternal in this fleeting cosmos, perhaps it's that cycle of curiosity, the endless turning of questions into wonder. Diggers looked up and asked if infinity could exist. Herschel mapped it. Leavitt measured it. Hubble expanded it. Einstein curved it. And you, listening now, are still exploring it. Quietly, gently through thought. In a way, every human mind is a small observatory, a lens collecting the faint light of understanding, shaping it into meaning. You don't need a telescope to take part in the story of discovery. You only need attention, the willingness to pause, to look, and to let mystery in. When you sit beneath the stars, your mind does something astonishing. It stretches beyond the boundaries of your body, beyond the horizon of Earth, out into the endless night. In imagination, you travel farther than any spacecraft ever could. Thought itself becomes a kind of light, not one that illuminates objects, but one that connects them. Maybe that's what the universe has been reaching for all along, not just stars and galaxies, but awareness, a way to see itself, to feel its own beauty, reflected in the fragile consciousness of a small thinking creature. And perhaps, if you listen closely, you can hear that connection even now. The rhythm of your breathing, the pulse of your heart, they echo the same mathematics that shape the motion of planets and the oscillations of light. You are, in the most literal sense, the cosmos made self-aware. It's easy to get lost in the numbers, the billions of galaxies, the billions of years. But if you bring it down to this moment, to this breath, the infinite becomes intimate. You're not outside the story, you are the story. As we near the end of our journey, that realization becomes a kind of peace. The universe began in brilliance, expanded through time, cooled into silence, and now, through you, it wonders about itself. You are both observer and participant, question and answer, spark and reflection. When your eyes close tonight, the same atoms that once drifted through ancient nebulae will rest in quiet rhythm. The same darkness that stretches between galaxies will fold softly around you. The same light that first burst forth at creation will flicker gently in your mind's eye. As we drift further into the story, our path now turns towards stillness, toward the final reflection on what it means for everything to end and for nothing to remain. But before we go there, pause for a moment in this awareness. You are not separate from the universe you admire. You're its consciousness, its witness, and its dream. And so, our long journey through everything, through stars and silence, through the pulse of creation and the whisper of nothing, brings us here to the quiet centre of it all. You can almost feel it now, can't you? That steady hum beneath existence. The same calm that lingers when you finish a piece of music and the final note still trembles in the air. The universe has played its song, from the fire of the beginning to the slow widening of eternity, and now it rests, still vibrating with memory. It's strange to realise that all of this began from something smaller than a grain of sand. From that almost nothing came everything: space, time, light, and life. And in some way, everything still carries the signature of that first moment. Every star is a spark of it. Every atom is a syllable in its sentence. Every heartbeat, yours, mine, the world's, is a continuation of that rhythm that started when time began to flow. For billions of years, the universe has expanded, cooled, and changed. It has built galaxies, burned stars, formed planets, and dreamed itself into consciousness. But expansion is not endless brightness. Like an ocean after the storm, it is slowly settling. The galaxies drift farther apart, the stars age, and the spaces between them grow wider. One day, far in the future, there will be no new starlight. The cosmos will fade into a long twilight, its warmth stretched thin. But that ending is not sorrowful. It is the natural stillness that follows every act of creation, a pause so deep it becomes peace. The universe does not vanish. It simply becomes quiet enough to hear itself again. When you look into the night sky, you are gazing into that quiet, not the absence of sound or life, but the presence of balance. Every point of light you see has travelled across the ages to meet your eyes. Some of those photons began their journey before the Earth had oceans, before the mountains rose, before there was even such a thing as memory. And yet they found you here tonight. You are, in this moment, the meeting point of ancient light and present awareness, a small stillness through which the universe passes and sees itself. Perhaps that's what all this has been leading to. Not an answer, but a feeling that the greatest wonder of existence is not how much we can measure, but that we are here to witness it at all. For all its size, the cosmos is intimate. Every distant star, every particle in the void is linked by the same history. You carry that history in your body. The carbon in your cells was made in a star's heart. The oxygen you breathe was once part of a supernova's breath. The calcium in your bones was forged in the death of suns. You're not beneath the stars, you're of them. And maybe that's the truest form of peace, to know that even when everything drifts apart, you're still connected by matter, by memory, by light. When scientists talk about the far future, they describe a time when the galaxies will slip beyond sight, when the cosmic background will cool into darkness. They call it the heat death of the universe, though the phrase is misleading. It sounds tragic, but it's not a death at all. It's a transformation. The energy that once blazed in stars will spread evenly through space. The grand contrasts, hot and cold, bright and dark, will soften until everything is calm again. The universe will not stop existing. It will simply stop changing. In that eternal calm, every photon will still be moving, every atom still vibrating, but there will be no difference left to mark the passage of time. It will be a cosmic stillness so deep it will no longer need the concept of before or after. The universe will have returned to what it was in the beginning. Not nothing, but potential. And in that return, perhaps it will be ready to begin again. We can't know for certain whether there will ever be another spark, another birth of light. But maybe that's not the point. The story of the universe isn't one of perfection or permanence. It's one of transformation. It's about how energy becomes matter, how matter becomes life, how life becomes awareness, and how awareness in turn learns to find beauty in impermanence. You, listening now, are part of that beauty. The same curiosity that led diggers to imagine infinite stars, that guided Leavitt to find rhythm in light, that carried Einstein into curved space and Hubble into the expanding sky. That same curiosity rests quietly in you. It's what keeps you awake under the stars, wondering about everything and nothing at once. And perhaps that's what the universe has been reaching for all along. Not knowledge, but wonder. The ability to pause, to look, and to feel awe. If you close your eyes now, you can almost sense it. That vastness humming behind your thoughts, the soft weight of distance pressing against the quiet of your room. Somewhere, galaxies are still drifting. Somewhere, the faint echo of the first light still ripples through space. And here, within you, those ripples have found a listener. The stars, the atoms, the laws of physics, all of it comes together in this single, fragile awareness. That is the quiet center, not a place in space, but a state of being. The stillness within everything that moves, the silence that holds the sound. Maybe that's what nothing really means. Not emptiness, but peace. A fullness so complete it no longer needs to change. And so, as our story comes to rest, remember this. You're not watching the universe from the outside. You're a part of its unfolding. You're the pause between two breaths of eternity. Fleeting, yes, but luminous all the same. If your eyes are growing heavy now, let them close. The same darkness that fills the sky will fill the room, gentle and safe. The same silence that waits between the stars will settle softly around you. And as sleep begins to carry you, think of this. The light that reaches you tonight began its journey long before the earth existed. Yet somehow, across billions of years, it found you. It always finds you. Because in this vast, ancient, ever-expanding universe, you, small, warm, thinking, dreaming you, are the place where the cosmos becomes aware of itself. And that is everything.